What's going on, everybody? This is Mr. Diamond, and as you can see, we are still at home, and I'm going to be going through the notes for word chemical equations. Now, the notes themselves aren't going to be that long, and then since I'm at home, I can actually pause this, and then I'll switch over to the hand cam, and I'll do some hand cam examples in this same video. But we're going to be looking at word equations compared to the last section. So in the last section, if I click back, we had these balancing examples where you were given an equation and you just had to go in and fill in the numbers. Now, you probably had some experience with that in some of your other classes. If you did not, hopefully you found those pretty easy. Word equations, though, are going to be trickier because they're going to require you to use your naming skills to figure out what the formulas are before you can even start trying to balance them. And this is where that whole idea of everything building starts becoming really, really important, because if you can't name, you're not going to be able to do these problems. And if you get an incorrect formula from your name, you're going to end up with an incorrect answer, because that's going to change the amount of O's if you have the wrong polyatomic, or the wrong amount of metals if you get a wrong ionic equation, or if you misinterpret the prefix, you're going to have a wrong amount in a molecular name. So it's really, really important that you can do that before you move on to here, which is why, like I said, naming is probably the most important chapter for this class. If you can't do that, you're kind of going to be screwed the rest of the year. So there are a few aspects making them trickier as well. The most important thing that makes them trickier, beyond just needing to know the names, are called diatomic molecules. Diatomics are elements that exist in nature in pairs. They buddy up. So normally whenever we're describing like hydrogen in nature, if we say the word hydrogen, you first think of, okay, H. H is the symbol for hydrogen. But if you're dealing with something in nature, unless it specifically talks about it being an ion, hydrogen actually exists as H2. It exists as a pair bonded together. The same with oxygen, the same with nitrogen, fluorine, chlorine, bromine, and iodine. All of these elements in nature exist as diatomics. They exist as two atoms. Di means two, atom or atomic means atoms. So in any chemical equation, if it says combining hydrogen and oxygen, for example, you would need to remember that it says hydrogen, which means it's H2, and oxygen, which means it's O2. So anytime these pop up, now the way you can kind of help remember that, I think I have a periodic table around here. So one of the ways you can help remember that, if I hold this up to the camera and go the right direction, let's get it even closer. So you'll notice that they form kind of a little 7 almost. You have your nitrogen, oxygen, fluorine, chlorine, bromine, iodine. There's a little 7 they form, and that's 1, 2, 3, 4, 5, 6 of them. Then you just have to remember that hydrogen way over here on the other side is your other exception to that rule. Because it's always an exception, almost always at least. So these things, if they get mentioned, you have to remember that they are actually going to be diatomics. Now, the one other piece that's going to be a little bit less important for this chapter, but will become much, much, much more important if you plan on taking advanced science classes. We can also use symbols to represent the state of matter of the reactants and the products. So if you see a little subscripted S like this, that tells you that whatever you're dealing with is a solid. So in this case, Ca with a little subscript S tells you that it is solid calcium. A cursive L represents liquid, so this H2O with a little subscript L tells you that you're dealing with a liquid. The reason we don't use a number is because it could look like the number, or a letter just normal L is because it would look like a number 1, or there's a good chance it could. So this little cursive L helps us with that. For gases, we use the subscript G. And then for aqueous, which we haven't talked about really before, aqueous is a subscript AQ. Now, I don't think I'm going to go into detail about that just yet, but for a brief preview, aqueous basically just means dissolved in water. Think aquea looks like aqua, or aqua is used as water. Aqueous is dissolved in water. But like I said, I think we'll talk about that more later on. Okay, so this is going to be a practice equation. Nitrogen gas and iron 2 oxide react to form iron 2 nitride and oxygen gas. You have to write the equation and balance it. So I'm going to go ahead and pause the video because I have that power on my home computer. And we're going to switch over to hand cam, and then we'll pick up there and do this example together. All right, welcome back, everybody. We are now in HandCam. So, again, our equation was nitrogen gas and iron 2 oxide react to form iron 2 nitride and oxygen gas. Now, one of the first hints that you're going to want to use to help you out in this is figuring out what is going to be on the left side and what is going to be on the right side. So I normally wouldn't recommend doing it in this exact way, but just for this very first example and clarifying it. Nitrogen gas and iron 2 oxide react. So it's telling us that these two things are reacting. So I'm going to put a little, just as a reminder, arrow telling us that these are going to be on the left side. And they're reacting to form. So this is the actual part that tells us where our arrow is going to be. Iron 2 nitride, that's going to be on the right side. And oxygen gas, that's going to be on the right side. Now, I normally would not do this, but just to make it very clear where our pieces of information are coming from, I'm going to go ahead and do that. So now we're going to need to write it out. So first, you can add lines if you want to then go back and fill them in, or you can just leave spaces. Either one is fine. For this first example, I'm going to leave lines. Then afterwards, you can decide whether or not you would prefer to do that in your actual problems. So we have nitrogen gas. Nitrogen, if we look on the periodic table, is N. And then if we remember, this little 7 right here, this little shape, are all diatomics, which means that this nitrogen actually exists as a pair. It's in 2 whenever it is found by itself. Again, that's only by itself. Basically what's happening is 2 nitrogen atoms are trying to be stable. That's the goal of every single atom always, is to try to be stable. And so what it's going to do to try to be stable is it's going to say, well, if I'm a bunch of nitrogens floating around by myself, I can just find a second nitrogen and we can kind of bond with each other until something better comes along. We also know it's a gas, so I am going to be very thorough, and I'm going to put a little subscripted G, because we know that that thing is a gas. Let me try to make really wish it saved the settings on my document camera, so it would always be in focus, but I guess technology is just not that advanced these days. Let's see, move that out of the way. And let's try to focus it a little bit. I think that's a little better. Or maybe it looks the same. I don't really know. I think it looks a little better for me. Okay, so nitrogen gas, and so I'm going to put a plus, and I'm going to put a line. Again, we want to have space to go back and balance it. Iron 2 oxide. So now, instead of just writing my answer right here, I'm going to actually need to work out what that iron 2 oxide is. So iron is Fe. Oxide is oxygen. Fe is a metal, and if you're not sure about that, Fe right here is a metal. So that means that this must be an ionic compound. We also know that because it's got a Roman numeral. Now that Roman numeral tells us that this Fe has a positive 2 charge, and we wouldn't know that otherwise because it's in the transition metal section, so we don't have a rule for it. And then oxygen is right here. Oxygen has a negative because it's above to the right of the staircase, and it's a negative 1, 2. So we're going to put a 2 minus there. We're going to cross our charges. We'll get Fe2O2, which we can simplify to FeO. So iron 2 oxide is FeO. We're going to go ahead and take that, and we're going to put that into our equation. Now, it does not tell us in the problem specifically what form the iron 2 oxide is in, whether it's a metal, a gas, a liquid, or aqueous. So we aren't going to be allowed to make assumptions. You don't have to put any labels on there. And in fact, I probably wouldn't count off for this label here. But again, it's good preparation if you're planning on taking more advanced science classes where those things are going to become more and more important, and later this year where we will care about it a little bit more. All right, next we say reacts to form. So that's our Q. Then we're going to put our arrow there. And then we're going to leave a gap. To form iron 2 nitride. Well, we know iron is Fe, nitrogen is N. We know from the first time that Roman numeral told us it was a +2. This time this Roman numeral tells us it's a +2 as well. Notice that you can't just assume that it's got to be a +2 both times because it was a +2 at the beginning. It's because of the Roman numeral. This could have started as iron 2 and ended as iron 3, and it could have been a different type of equation. It would have been balanced differently if that was the case. Just because iron has a +2 at one part does not mean it has a +2 for the whole problem. But in this case, because they both have a Roman numeral 2, we know that iron must have a +2 charge. Now, for nitrogen, we go check the periodic table. Nitrogen is one step further to the left, so it's going to be negative because it's above to the right, and it's 1, 2, 3 steps away, so it's going to be -3. We're going to cross our charges. We get Fe3 in 2. We cannot reduce that, so we are good. It is as simplified as it can be. Fe3 in 2. Then we'll put our plus, so iron 2 nitride, and we'll leave a gap so we can go back and balance it. Oxygen gas. So oxygen is O, but you have to remember oxygen is in that chunk right here. It's in this section right here. It's in this little 7. The other way that I actually ended up remembering it wasn't because of the whole 7 thing. That was what one of my students last year pointed out to me, is how they remember it. I just remembered it was the halogens plus the really common gases, because hydrogen, nitrogen, and oxygen are just the 3 gases that just seem the most common to me. So if that works, you can use that. But somehow remember, or make sure you remember that hydrogen way over here on this corner over here, nitrogen, oxygen, fluorine, chlorine, bromine, iodine are all diatomics. So we have O2 instead of just O. All right. Now, to balance this, and I don't actually know if I have a pencil here at home. That would be unfortunate because I prefer to do these in pencil. Let me check my bag. Nope, I don't seem to have a pencil. So there's a bunch of different ways you can go about balancing this. My preferred method, I believe I showed you the last time, involved using just kind of working it through as you go and make changes as needed. But to do that, you really want to have a pencil. Otherwise, you're going to be doing a lot of scratching out with pen. I'm going to be using a pen, so I'm going to have to scratch them out if I end up needing to fix anything. So we'll start with nitrogens. Nitrogen is in 2. This is in 2, so that's good. This is Fe. This is Fe3. So to fix that, I'm going to put a 3 there. N2 still balance. 3 Fe's, 3 Fe's. 3 O's. Well, I can't get this 2 to become equal to 3 O's, so I'm actually going to have to back up and fix this. The lowest thing that a 3 and a 2 have in common is 6. So I'm going to multiply that by 3. I'm going to multiply that by 6. That's going to require me to multiply this by 2, because I need to get 2 times 3 is 6 Fe's, 6 Fe's. And then 2 times 2 is 4 N's. So I need to get 2 more N's. Now, I know that process, again, goes a little bit fast, but that's kind of supposed to be the easy part on these. If you still need trouble or have trouble with this and need a little practice or need a little help, please let me know. I'll be happy to help talk you through it. But from my experience, I think a lot of people find this part to be kind of the easy part. Getting the equation is usually the hard part. So I'd rather spend more time focusing on that one. But don't feel bad if you struggle with it. It is kind of a whole bunch of jumping around in the problem. If there's any other method that you've used in the past to balance an equation, though, you are more than welcome to use that if that makes more sense to you. Now we can do one quick double check. So first, 2, 6, 2, and 3. All of those can't be reduced to anything. Then there's 2 times 2 is 4 nitrogens, 6 irons, 6 oxygens. 2 times 3 is 6 irons, 4 nitrogens. 3 times 2 is 6 oxygens. So all that is balanced, which means this is our final balanced equation. Now notice we had to go through, use our naming skills, know what the names of these things were, and only after we did that were we even able to start trying to balance the equation. So if you don't know how to do the naming, you really couldn't even start this problem very easily. Also notice if you would have messed up, for example, if you would have said, well, iron 2 means Fe2 oxide, Fe2O, you would have ended up with a completely different answer for this problem. So make sure that you are avoiding those mistakes. Any error at any part of this can lead to a kind of a cascade effect where you'll keep messing up further and further down the line because you didn't have it correct at the beginning. All right, that's going to be the end of this video. If you have any questions, please shoot me an email. Otherwise, this is Mr. Diamond signing off. Have a good rest of your day, everybody.